Okay, systems of equations, the next section in Chapter 8. Recall that way back at the beginning of the course, we mentioned that Descartes was the person who came up with a way of showing that you can either solve things geometrically or solve things algebraically. And this is what we're going to show today. Suppose you have these two lines. Do you agree these are both lines? Anything of the form ax plus by equals c, recall, is a line. So those are both lines. And if we wanted to graph them, we could. And what we're after is finding a point of intersection of those two lines. Quite often in the real world, we have problems. We'll do at least one example of this, where you have a couple equations like this. It's called a system of equations, and you want to find the value of x and y that satisfies both of them. So how do we solve these? Let's see. X plus 2y equals 9. Maybe the easiest way is to say, well, if y is 0, x would be 9. Right there. And if x is 0, y would be, if x is 0, y would be what? 9 halves, which is 4 1/2. 1, 2, 3, 1, 2, 3, 4, 4 1/2 right there. So here's the line that goes through those 2 points. X plus 2y is equal to 9. And now we have another line. 2x minus 3y equals 4. If y is equal to 0, x would be 2. So there's a point on the line. And if x is 0, y would be what? Y would be negative 4/3. Here's negative 1, there's negative 2, negative 4/3 would be about like that. So it goes through those 2 points. So it looks something like that. So it looks like they intersect someplace right about there. It's hard to know exactly where unless I draw the lines very precisely. And even then, it's not easy to get it if the point of intersection is a couple of extended fractions, things that have a decimal. You could have, the point of intersection could be a place 3.149361174, something like that. Well, you're not going to find that by graphing the lines. So let's see if we can find another way. There's a couple ways to do it. One way is called elimination. It's called the method of elimination, where you get rid of one of the variables first and you solve for the other variable, and then you solve for one and then you can solve for the other. So the easiest would have been if I would have had something like x plus y is equal to 5 and x minus y is equal to 2, and then if I just add these two equations together, notice I'm going to get 2x is equal to 7, and then x is equal to 7 halves, and once I have x is equal to 7 halves, I can find out what y is. Let's see, 3 1/2, then y would be 3 halves. Right? So there's just a simple one I just made up. So that's called the process of elimination, where you get rid of, by adding the equations together, you get rid of one variable, you solve for the other one. Once you have x, then you can go back in either one of these equations and get the other one. I use this one, but if you have 7 halves and you solve this one for y, you're going to get the same thing. 7 halves minus 3 halves is equal to 4 halves, which is 2. So that works out very easily. This system isn't quite as convenient. I'm going to have to do a little manipulation in order to do it. So that one, I had the same number of y's in each equation. Here, notice that if I multiply this equation by 3 and get 3x plus 6y is equal to 27, agree, if I multiply that one by 3, I'm going to get that. And then if I multiply this one by 2, I'm going to get 4x. And and here I multiply this by 2, it's going to be minus 6y, and I multiply it by 2, I'm going to get 8. To see that? You see why I did that? By multiplying this one by 3 and this one by 2, I get the least common multiple of those two, which is 6, and so they both add up to 6, and now I'm going to be able to just add them together. See this? So now I add them together, and I get 3x plus 4x is 7x is equal to, those go away, which is the whole point, is equal to 35. So x is equal to 5. Once I have that x is equal to 5, I can easily get this. I can just go 5 plus 2y is equal to 9. So 2y is equal to 9 minus 5, which is 4. Y is equal to 2. So apparently the point of intersection is the point 5, 2, which looks pretty close to what I have right there. See that? So it's called, that's very simple, straightforward. It's called the process of elimination. You wouldn't have had to eliminate y, you could have eliminated x. How could we have done that? If I had multiplied this equation by negative 2, then we would have gotten negative 2x minus 4y is equal to negative 18. There's the whole equation multiplied by negative 2. Now leave this one just as is. And again, now I can just add these two together, and I have no x's, and notice I have negative 7y is equal to, if I add these together, I'm going to get negative 14. So dividing both sides by negative 7, I get y is equal to 2. Once I have that y is equal to 2, I have x plus 4 is 9. That means that x has got to be 5 again. Okay? Obviously, you need the same answer both ways. So you can get it either way. Okay? So you can do it either way there. It's called the process of elimination. Here's another way to do it. I think that way is the easiest and just the most natural. But here's something else you can do. If you wanted to, you could solve both of these for whichever variable you want. Let's solve them both for y, since that's typically what you do. So if you set the first one equal to y, you're going to get y is equal to 9 halves minus x over 2. Can you do that amount of math in your head? I brought this over to the other side, so I have 2y is equal to 9 minus x, and then I divided both sides by 2, which is going to give me 9 halves. And then I have the x over 2, which is going to be right there. How about this one? I'm going to need a little help on this one. I'm going to do this in a couple steps. I'm going to go 2x minus 4 is equal to 3y. I brought the 3y over to this side and the 4 over to that side. And now I'm going to divide everything through by 3. And I'm going to get y is equal to 2/3 x minus 4/3. Okay? So now that they're both set equal to y, now I can just set them equal to each other. See that? So they're both set equal to y, so now I can just take 9 halves minus x over 2 is equal to 2/3 x minus 4/3, and now it becomes something that, like what we did in chapter 5 or 6, I think, as I recall. Let's get rid of the fractions by multiplying everything through by 6. Both sides, if you multiply everything through by 6, your 6 divided by 2 is 3. 3 times 9 is going to be 27. 6 divided by 2 is 3. Here you're going to get negative 3x. 6 divided by 3 is 2. 2 times 2 is 4, so I'm going to get 4x. And then finally, 6 divided by 3 is 2. 2 times 4 is 8. So now you have that. So now I can add 3 to both sides and get 7x. And I can add 8 to both sides and get 35. And so there again, I have x is equal to 5. And then as before, you can go and get y. So you can see why I prefer the other method. This one was, I think, quite a bit messier. You have fractions and that sort of thing. It still works though. And sometimes, especially if you already have two lines that are solved for y, then it's easiest just to go ahead and set them equal to each other. Okay? So that's another method. And yet another method, which really amounts to the same thing, is to take one of these equations and let's just solve this one for x. So this one right here gives me what? X is equal to 9 minus 2y. Do you agree? 9 minus 2y. And now that that's x, I can just substitute. This method is called substitution. Now I can just substitute this x in for here. So I'm going to get 2 times, every place I see an x, I'm going to get this. 9 minus 2y minus 3y is equal to 4. And so now you get 18 minus 4y minus 3y is equal to 4. Here I have negative 7y, so I can bring them over to the other side and get a positive 7y. And here I'll subtract 4 from both sides and get 14. And so I get y is equal to 2, as before. So now you can go and get x. So that's called substitution. So the point is, you should be aware of all these methods just so you can use whichever one is the most convenient. And so you have your choice. And what else was I going to say? I guess that's it. Okay. So so you get your choice of which one you want to do. There you go. Okay, very good. So that's called systems. So once you have 2 equations, you can easily solve for both of the variables. Now let's see once where this is used in some practical situation. The author has lots of them in the book. I'm just going to do one. They're all kind of the same sort of thing. Suppose you have a group of people, office friends, and they go out for lunch together. And on day 1, 3 of them have salad, and 5 of them have wraps. We'll say they're wraps. And the total is $103 for all 8 of them. And on day 2, 6 of them go. 2 of them have salad, and 4 of them have wraps. And the total that day was $78. And all they knew was the total, and it occurs to them that they'd kind of like to know how much each of those things cost. Okay, so how can we do it? Well, remember, can you anticipate what I'm going to say? Let. You need to take a physical situation, and the way you turn it into something mathematical is by letting x be something and y be something, whatever you want. So let's let x be the number of salads, and let's let y be the number of wraps. Okay? And so once we have that, we're on our way to solving the problem, because on the first day 3 people had the salad. Oh, no, I'm sorry. We already know the number of salads and the number of wraps. Agreed? What we want is the price. Okay, there you go. See that? I had to look back up and realize, no, that's not what I want. I want x to be the price of the salads. And I want y to be the price of the wraps. Agreed? That's what we don't know. That's what we're trying to find. So, see that? That's where you catch yourself. You catch yourself quite a bit. You make a mistake and say, no, no, no. You look at it again and say, that's not what I want. So, x is the price of the salad. So on the first day, 3 people had the salad. So 3 people times that price. And then you had 5 people that had the wraps. So you had 5 people that got the wraps, and each one of those was y dollars. And so by the time you put that all together, you're at 103. Agreed? And on day 2, you had 2 people that had the salad, and each one of those was x dollars, so you're going to get 2x is the total price for the salads. You had 4 people that had the wraps. Each one of those wraps cost y dollars, so 4 times y this is the total price for the solids, that's the total price for the wraps. Add all that together and you get 78. See that? So this would be one I couldn't really, we could graph it, but it's much easier just to do it algebraically. So I like to use as small numbers as possible, so I'm going to multiply this one by 2, and going to get 6x plus 10y is equal to 206. Agreed? If I multiply that whole equation by 2. And then I'm going to multiply this one by negative 3. And negative 3 will give me a negative 6x. Negative 3 here is going to give me a negative 12y. And negative 3 times 78. What's 78 times 3? 4, 210, 234. So a negative 234. So now I can just add those together. And I'm going to get a negative 2y on this side. And on this side, what's the sum of these two things? The way to do that is to go 234 minus 206 is going to be $28, so it's going to be a negative 28. And now you can divide both sides by negative 2 and get y is equal to 14. Once you have y is equal to 14, you can use either one of these to find out what x is. So let's use the top one. If you use y is equal to 14, 14 times 5 is 70. So you're going to get 3x plus 70 is equal to 103. So 3x is equal to 33. So x is equal to 11. And again, I chose numbers. I made this problem up a couple days ago. I chose numbers that worked out real nicely, but they wouldn't have to, right? You could have 11.37 cents or 14, whatever. It might not be near as nice, but you can still do the problem the same way. So there you go. Now you should always check it just to make sure you have it right by checking the other equation. If you check the other equation, I'm going to get 22 here. And then 4 times 14. 2 times 14 is 28. 28 times 2 is 56. So 56 gives me, sure enough, gives me 78. So there you go. So that's all there is to it. The thing I should mention before we go is, will there always be a solution? Let's look at lines and see once if there will always be a solution. What if I give you, just as a very easy example, x plus y is equal to 5, and x plus y is equal to 7. And let's see once what happens if we solve that system. What do we get? Well, I can take this one and leave it as is. And I can take this one and multiply it by negative 1. And then add them together to get rid of the y's. And when I get rid of the y's, notice what happens. I also get rid of the x's. And I get the nonsense equation that 0 is equal to 2. How can that be? Well, that can be because if you were to graph these two, you're just going to get two lines that look like this. Notice that there's no point of intersection there at all. They're parallel lines, so there's no solution. And so that's what happens when you have parallel lines. You'll get no solution. The other kind of crazy thing is if you had 2x plus 2y is equal to 10, then by the time you finish it up, you're going to get what? You're going to get x plus y is equal to, let's take this one right here, 2x plus 2y is equal to 10. Multiply this one by negative 2, and you're going to get negative 2x minus 2y is equal to negative 10. Add both equations together, you get 0 equals 0. And that's the case when basically both of those equations are giving you exactly the same line. So in this case, the first line looks like this. And the second line, if you were to graph it, you can just divide everything here by 2 and you get exactly the same line. So that's why all values of x and y satisfy both. Any pair that satisfies this also satisfies this. So there's no one unique pair that satisfies both of them. Okay, very good. So that's all there is to do with lines. And In the next video, we're going to use this to solve a really interesting problem called using something called linear programming, something which was developed just in the 1950s or so, in order to try to help the United States be more efficient in producing equipment for the World War II effort. So it's kind of recent mathematics as far as mathematics goes. Okay.